In this video, we're going to talk about paired samples. Coming out of section 5.1, we learned about the T procedures for testing hypotheses and constructing confidence intervals for one population mean, assuming the standard deviation was unknown. In section 5.2, we're going to take a look at an experimental situation known as dependent samples or paired samples. And our objective here is to actually compare two population means. So we haven't done that yet. This time we want to actually compare two population averages. So it's important to note that these samples are not independent samples. Usually we have independent samples, but this time the two samples are not independent, or we can call them dependent samples. Now we can create dependent samples by virtue of our experimental design. Okay, so when we talk about paired samples here, that means we have really one set of experimental units. The experimental units are actually the objects or subjects that we apply a treatment or some kind of experimental manipulation to them. So the experimental unit, for example, could be a car, it could be a plot of land, it could be a person, it could be a house, whatever that might be. It could be individuals, or it could be just subjects or different objects. So again, our design here is called a paired design or dependent samples. Now, here I've given you a few examples of situations where we have or we can assume paired samples. In our first example here, we want to see how effective a diet is. So what we're going to do is we're going to measure weights of individuals, possibly before they go on a diet and also after they go on a particular diet. So notice here, diet is our experimental manipulation here, or our treatment that is applied. So the diet would be a treatment here. And it would make sense that we measure on that same individual. So for example, myself, I would go on a diet. So they could measure my weight before I go on a diet, and maybe a month, a few weeks later, measure my weight again after I go on the diet. And the idea of using the same experimental units, of course, is to remove the subject to subject variability. It wouldn't make sense to measure, for example, the weight of 10 individuals and then look at 10 other individuals that are comparable in weight, let's say, to them, and put that second group on a diet. It just wouldn't make sense to do that. Here's another example. The second example is, let's say we want to measure the carbon monoxide emissions before increasing the oxygen in the fuel tank and after doing so. So in other words, before there's no oxygen in the fuel tank, we're not gonna add any oxygen in the fuel tank, but then afterwards we're gonna actually increase it. So there is some oxygen in the fuel tank, it's just we're gonna increase it afterwards by a certain amount. And then measure the carbon monoxide emissions. Another example, let's say we want to compare the social attitudes of twins. Notice in here that we have, with twins, we actually have two different subjects, but we're going to treat them as one cohort, as one sample. Because especially with identical twins, at least physiologically identical twins are just that, identical. So we can detect we can detect any differences in the treatments due to the treatment effect, not due to the variability from subject to subject. That's the advantage of pairing them. So in the case of twins, we're going to look at the social attitudes of the twins. So let's say one child's going to stay home with their family, the other one's going to be sent away and live with a minority family, and a few weeks later you can compare the scores on a questionnaire and compare those scores to one against the other. Another example, let's say we want to compare the ages of married couple. So here again, married couple, they're not really the same subjects, are they? So the idea here is that, well, each couple makes a cohort, so that's going to be paired together as one sample, because we're interested in comparing the mean age within that cohort or within that experimental units. So here the mu1 would be the average age of all married men, mu2 would be the average age of all married women. And let's say we may be interested in knowing whether on average men are older than women in a marriage. Here's the other example I have for you. This should be the end of it. Yeah, okay. So here's the other example I have. Suppose we have two fertilizers, fertilizer A, fertilizer B, and we're going to apply these fertilizers on the same plot of land. So notice we're removing location to location variability here. And we're going to measure the yield of crop from these two fertilizers. In fact, the word treatment came from that. I believe it was Sir Ronald Fisher. We learn about the F. Fisher's distribution when we talk about ANOVA later on in this week's lectures. He's the gentleman, again, Sir Ronald Fisher, is that coined the term treatment. Because a lot of times in agricultural studies, the treatments are actually like fertilizers. It could be potash, it could be different chemicals that they would apply to a plot of land, and then to try to measure the yield of crops. And finally, the last example I have here is, suppose we want to compare the rest pulse and run pulse on the same subjects. So example, for instance, myself. They could measure my rest pulse at rest. Let's say my pulse is 60 beats per minute. And then I'm going to run around the block or around the house or whatever the perimeters. I'm going to run some distance and then come back and measure my run pulse. Again, I'm the same subject, so it would be accurate. And any difference, let's say, between the rest pulse and the run pulse will be attributed to running here. So I can measure the effect of running on pulse, a person's pulse. So why pairing? I kind of alluded to that earlier. There you go. Because pairing removes variability between each group. So as a result, as a consequence, we have a smaller sampling error. And when we have a smaller sampling error, that's a good thing because it enables us to detect differences between the averages due to the treatments actually. So we can look at the treatment effects. So it's the removal of that subject to subject variability. Now the conceptual design here, I'm going to have like, I think 4 or 5, 4 of them. So let me not convolute it by going too fast. There you go. So here's actually conceptually how this paired design goes. We're going to assume that we have two populations that are normally distributed. Each of them have, now random variable x is the same measurement. Okay, same variable on the two populations. So for example, these could be weights. So these are all the weights of individuals before they go on a diet. These would be all the weights of those individuals after they go on a diet. Could be millions and millions of them. So this first population is going to have its own mean, its own deviation. The second population will have its own mean, its own deviation. And then what we're going to do is actually we're going to pair them together, correct? So how are we going to compare the average between two groups? Well, the best way to compare them, and I have that coming up, how are we going to do this? What's going to represent how do we compare the two averages? So once we have these two individual populations, we're going to pair them together, and then by pairing them, we're going to actually, the way to compare the two averages in the mathematical engine behind it is to actually apply differences here. We're going to look at differences between scores before and scores after. And that's how we're going to compare the two averages. Now, what's unknown here is mu d. I just want to make clear that this is what we're shooting for, the average difference. And depending on that average difference, that's how we're going to compare the means. And that's coming up. I'll explain more on that. And then, according to central limit theorem, what we're going to do is we're going to take, let's say, hypothetically repeated samples from that population of differences, and then we're going to have the sampling distribution of d bar. In other words, we're going to look at the average difference when we compare the two averages up in here in the population. And according again to central limit theorem, that distribution is going to be normal if we sample from two populations that are normally distributed, and it's going to be approximately normal if these two populations up here are not normal, given with these parameters. The average of the average difference, the center of the sampling distribution of the average differences, is going to be exactly what we want to estimate. But its a standard deviation is going to be less than that. Okay, so in here what I have is that a point estimate of the average difference is d bar. In other words, if you want to know what is the average difference in the population, use a sample and look at the average difference in the sample. That's what that means. And then once we actually reduce these to let me actually erase this part here so you don't get confused there. So what the effect of differencing between the two before after scores is to create one sample. We in effect reduce it to just a sample with just differences, and then we're going to do a one sample t-test on those differences. Okay, now I'm going to actually show you how this is done, and of course we're going to do this in Minitab. So here's an example of how we want to do this. In this example, it's a very interesting example, in fact. So here is just introduction to this example. Anorexia nervosa is a serious eating disorder, particularly among young women. The following data provide the weights in pounds of 17 anorexic young women before and after receiving a family therapy treatment for anorexia nervosa. And here's the citation. So you can notice our sample is small, and we have really one set of subjects, right? These 17 anorexic young women. But we're looking at their weights before and after. So we don't have really two independent samples. We have one sample, dependent scores before and after. So here are the weights of these individuals before, and these are the weights after family therapy. So just to kind of looking at some of these, and I have this also in Excel, in fact, right in here. Okay, and I'm going to be typing these up. In fact, I have already in Excel. I'll be taking them to Minitab, and we're going to run them in Minitab. But I just want to show you, same set of scores are right in here. So these are the 17 subjects, their weights before, their weights after. Now, if you look at, for example, subject number 1, his or her weight, these are young women, right? Yep, so these are all women. So this person, her weight before is 83 pounds. That's pretty light. And of course, afterwards is 94.3 pounds. So looks like therapy actually helped this individual. She gained some weight. How much? To the tune of 11 pounds. Okay. Now, one thing here I want to point out. A negative difference is actually the desired outcome here, right? We're hoping that these people gain weight after following family therapy. Okay. So a negative 11 actually is a good thing. So here I have it, negative difference means higher weight after therapy. A 0 difference, like I have almost here. Look at subject number 7. 76.9, 76.8, almost. It had no effect on this person. 0.1. Don't worry about these squares. This is if you want to do this by hand. But I just have them there, so ignore this last column. So let's see, 0.1. So if this was 0, that means it would have been identical. I don't have any 0. That's the closest to 0 I came on that one. And what about the positive difference? A positive difference means a lower weight after family therapy. Look at, for example, this one right in here, 2.9, almost 3 pounds. Before, this person weighed almost 80 pounds, after almost 77 pounds. It's a positive difference, so it means a lower weight after. Therefore, if you want to know the effectiveness of family therapy, we're hoping for what? We're hoping for these negative differences, right? Means higher weight afterward. I have my happy face emoticon here. Okay. Or actually, that's my emoji, not the emoticon. Sorry. Emoticons, you do them from the keyboard, right? Using dashes and semicolons, things like that. Anyhow, now for this exercise, by the way, I didn't read the rest of it. Here's the burning question. Does family therapy appear to be effective in helping anorexic young women gain weight? Perform the appropriate hypothesis at 5% significance level. And there's a follow-up exercise for this where we want to actually construct a 90% confidence interval. Okay, so now in order to set up our hypothesis, which we will in a minute, but before we do, let's take a look at this. Remember, to establish effectiveness of family therapy goes back to what I have here. A therapy is effective for them to gain weight if the negative difference occurs, like here, 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 here. These are all positive. Wow, look at this one, 21 pounds. This really helped this individual. And it looks like overall, all in all, look at that. The total average is negative 123. If you divide that by 17, you get the average weight gain. So it looks like pretty good. So we're looking, but the point being, we're looking for negative differences. Means less than 0, right? Negative difference, less than 0. So if the average difference is 0, means before and after there's no difference. If the average difference is less than, in this case, less than means negative, that means the therapy is effective. So how are we going to do this? This is actually a paired t-test procedure. We have these assumptions. We always have the assumption of simple random. This time we have, notice, paired sample. We don't have two individual samples. So we have a simple random paired sample. The differences we assume are normal. Okay, normal differences, or sample is large. That means greater than 30 pairs. And of course, our null hypothesis says there is no difference between the averages before and after anything. The alternative, of course, could be any one of these. In the case of these anorexic young women, the middle one is what we want, right? Weight before is less than weight after. That's what we want to show. Which the other side of that coin is that the weight after, mu2, weight after, exceeds weight before. So the middle is what we want to do. This is our test hypothesis, test statistic. If you want to do this by hand again, and here are our decision criterion, if you will. There are two approaches to hypothesis test: critical value, p-value. We're just going to stay with p-value approach. Okay. Remember, p-value less than alpha, we reject the null. And that was for hypothesis test. Okay, now the paired T confidence interval procedure has the same assumptions. And this is again the formula that you see for the confidence interval. And that's it. Okay, so going back to our anorexic young women, so I'm going to let mu1 be the average weight before, mu2 the average weight after. So I have written the null hypothesis 3 ways. 1, the average difference is 0, means family therapy is not effective. Alternative, remember, we want the average to be negative, and negative means higher weight after therapy. Or you can say mu1 minus mu2 is 0. Here we say mu1 minus mu2 is less than 0. And if you move mu2 to the other side, you get mu1 equal mu2. So all 3 of these are really telling me the same thing. And all 3 of these are telling me the same thing also. If mu1 minus mu2 is less than 0, that means mu1 must be less than mu2. That means their difference must be negative. Okay. And this is the run from Minitab. Okay, I'll go to Minitab and actually show you how this is done. So we're doing a pair t-test and confidence interval for weight before, weight after. These are some descriptive statistics for those raw numbers that we saw up there earlier. The weight before was 83 on average. Afterwards, they gained on average almost 7 pounds, right? A little over 7 pounds, 7.2.3-ish. These are the deviations, of course, and this standard error, SE, means the standard error of the mean. This is like your sigma over square root of n for each of the before scores and after scores. Okay. And of course, our test hypothesis here, null hypothesis, the average difference is 0, meaning no difference against the alternative less than. Our p-value turned out to be rounded to 3 decimal. Minitab rounds it to 3 decimal. To 4 decimals, I believe this turned out to be 0.004, something like that. But anyway, our test statistic is -4. You can think of this as like -4 standard deviation below. Not quite 4 deviations, but pretty darn close to it. So we have seen an unlikely event, and therefore we're going to reject the null hypothesis. Remember the null up here? Null said there is no difference between the average weight before family therapy and after family therapy. So we're going to reject that null and say no, family therapy is indeed effective. And this is the confidence interval. Confidence interval. Always when they say construct confidence interval, they're thinking two-sided confidence intervals. We could do one-sided confidence interval, and I'll make a comment when we go to Minitab about that. But you got to make sure that you do a two-sided confidence interval here. And there you go. You see that average gain of 7 pounds. But look at the deviation is almost equal to that. So that means it's pretty widespread. And the average difference, 90% confidence interval, the average difference runs anywhere from -10 to -4 pounds. Remember, negative means a good thing, right? So that means on average, these anorexic young women following family therapy gain anywhere from 4 to 10 pounds, right? And here what I've done is I'm testing that assumption, the normality of differences. So here is actually histogram of differences. Now this is how Minitab does it. Minitab says, see your null hypothesis, your hypothesized difference is here 0. And X bar is a point estimate of the true average difference here, which is about 7 pounds. So we actually look at this one. Don't worry about the hypothesized. So there you go. Looks like distribution of differences is almost normal. And to the right of that is actually a box plot. Look at the box plot. It looks almost symmetric. For this to be the box plot of a normal distribution, this middle line, which is where the median is, should be in the middle. And that would have been exactly almost like a normal distribution. Okay. So we feel pretty decent about running a t-test. Although the t-test is fairly robust to moderate departure from normality. So it's, but still. Okay, now let's see. So what's our conclusion here? Let me shorten this a little bit. Okay, so here's our conclusion. One is that on average, we're going to decide that family therapy seems to be effective in gaining weights, right? About by the tune of, again, 7 pounds. The observed significance level here, which we call the p-value, which is the actual observed probability of a type 1 error here, is 0.0004. Now remember, Minitab gives it to you in to 3 decimals, so I actually ran this on a different software, and I got this 0.0004. And I have a note here for us. Just because we reject a null doesn't mean we could be right. We still could be wrong. Okay, so we could be making the wrong decision, but to look at the odds, not the odds, but the probability that we are making a bad choice here, a bad decision. 4 in 10,000 chance that we made the wrong conclusion when we said reject the null hypothesis. Okay. Now, also according to the confidence interval here, it looks like, because that -4, -10 to -4 range, we are 90% confident that the family therapy on average actually helps these women gain anywhere from 4 to 10 pounds. That's what the confidence interval tells us. Okay, so let's see how we're going to actually get these numbers off of Minitab. Now, in order to do this, let me actually, I may have to pause. Let me bring up Excel here. Yeah, let me put this in. No, that's okay. I guess I'm okay. I'll sing as long as I can without having to resize my recording window. Okay, so don't worry about this one. This is our next exercise, but this is the one that we're looking at right now. You see how I actually input the data into Excel. I'm just showing you how to do this. You can directly type these into Minitab, but you can, I just want to show you how you just bring it in from Excel, just to be different. So these are the actual weights. I typed them in before and after. You see that? These are the 17 scores. I know I'm in row 18, but because I had a label up here, see my cell 1, my first record is actually a label. So those are the 17 scores before and after, right? That's what those are. So if I want to take these to Minitab, I'm going to highlight these. I'm left clicking and holding and dragging, and let go of the left click. And I can do Control C. That means I want to copy this. And then I'm going to go to Minitab. And here's Minitab. Now let me resize my window here in Minitab. And there you go. That's Minitab. And let me make sure again. I want to make sure I'm doing this right, folks. There you go. That's what I want. Okay, perfect. Now you can see the entire viewing screen with the Minitab. Now remember, this is our one sample t-test that I did from previous lecture. So, okay. Now in order to do today's lecture, I'm going to go to this cell and Control V. There you go. Control V is the shortcut for copy paste. And here you have weights before and after. They're all in here. See that? All 17 pairs are there. If you want, you can create a column of differences here, but again, there's really no need for what we were doing here, because we're just interested in the output. But that's how you input it. Pretty easy, huh? And let me actually delete this so it's not distracting you. Okay, so this is what you should have. Now, in order to do a paired t-test, we're going to go to Stat, Basic Stats. And then we're going to go over, come down, down, down to paired T. And if you hold the mouse over there, it gives you a brief description of what that procedure does. Okay, so here's your pair T. You're looking at the dependent groups, and you left click once on that. And here's what the options are in that drop down. Each sample is in a column, or do you have summarized data, which I don't. But if you did, let's say create a column of differences, that's how you would point to that. For example, see that? Summarize differences. I would say my sample size is this, my sample mean is that, deviation. These should be differences though, not for individual samples. And we don't have that. We actually have data in columns. Now if I just left click, notice there's nothing here on the left pane. So in sample 1, if I left click once, you see these columns appear. So I'm just gonna, you can left click once on weight before and select it. For the second one, I'm gonna do it different. Sample 2, I'm just gonna double click on this and bring that inside to activate that as our second column. So now let's go to our graphs. And here's how I got the histogram of differences, and here I got the box plot of differences. Okay, individual value plot of difference, you can activate and see what that looks like, but I'm just going to check these two. Okay, now I go to options, and in here this is where you actually determine the confidence level. Hypothesized difference for us was 0, means no difference. And this is the alternative hypothesis. Now, let me go less than. I'm going to test the hypothesis. I don't care about the confidence interval yet. I just want to do my hypothesis test. Less than. So this 95 doesn't matter, but I'm going to leave it like that. Hit OK, and OK again. And then you'll see the output. And again, this is the output that I had in my note. Oops, sorry. And there you go. So these numbers should be familiar. These are the descriptive statistics. And here's our test statistic that we had. This is our p-value, and that's our t-test for differences less than 0. This is your histogram of differences. And here's your box plot. Okay, now if you look at what I had in my OneNote, what's under here looks different than what it is in here. Because this is a left tail test, what Minitab does is actually constructs a one-sided confidence interval. So this is what a one-sided for left tail confidence interval looks like. It runs from almost -5 all the way to -infinity. You see that? So it gives you the upper bound, but there's no lower bound because your alternative is less than. We don't usually do that with our confidence intervals, okay, just to mention. So, and this is H naught here. That means the hypothesized value is right in here. You see that 0? So it shows you the position of this histogram relative to hypothesized value of the mean difference. And it's trying to give you as much information as possible. Sometimes it may be information overload, too much information that could be misleading and may create confusion for us. So there you go. Here is the box plot. Now you can ignore, there you go. Look at the box plot without the lower part. And the box plot shows almost normality of the differences again. See that? Now, notice up here, let me go back here now. This confidence interval, notice there is upper bound, but there's no lower limit on it. Right in here should be a lower limit. That lower limit is -infinity right now because we're doing a left tail test right here. So that's why the part of the question that said construct a 95% confidence interval, I'll show you how to do that now. So now we want to do the confidence interval. So I'm going to go to stat, basic stats. Let's go back to pair T. And we have all of this data in here already. And now my focus is on a 95% confidence interval. We're done with the hypothesis test. We want to construct confidence interval. To get the correct confidence interval with both upper and lower limits, we need to change this alternative to not equal to. So this way, it's going to give us a lower limit and an upper limit. Hit OK. And we don't want the graphs anymore. And oh, let me actually put the put it just to show you how different it's gonna look like, the lower part of the box plot. And there you go. See, here's our 95% confidence interval, and actually now you have a lower limit, upper limit. That's what I had in my notebook. Okay, so the true average weight difference runs anywhere between about 4 to 11 pounds here, based on 95% confidence. And here's your box plot. And remember, before this, the line below the box plot went from here all the way to the left. There is a left arrow. It was running to negative infinity. Now it's not. And this is your actually confidence interval, and this is your box plot. So the shape of the box plot, notice, didn't change. It's just this label changes. And that's all we wanted to do with this example. Now, let me actually go back to the other example that we had. We're going to change that. We're going to look at the second example, folks, to help you do this in StatCrunch. I'm sorry, in Minitab. I use too many software, so I get confused to which one I'm working with. Okay, and I think this should do it. Let me focus it on over here, and that should do it. Okay, good enough. Hold on. Sorry, folks. And there you go. Okay, so what we want to do now is we want to look at our last example here. Okay, now this second example is actually interesting as well. For the second example, this one has to do with glaucoma. Now remember, glaucoma is not a good thing. As it states here, glaucoma is a leading cause of blindness in the US. So the researcher here measured the corneal thickness of 8 patients who had glaucoma in one eye but not in the other. So note in here, we do not have 2 independent samples. It's the same subject, same individual, whose corneal thickness was measured in one eye and also in the other eye, the eye with glaucoma and the normal eye. So all of these subjects must have had one normal eye and one eye with glaucoma. Now, whether it's right eye, left eye, it really doesn't matter. The direction doesn't matter, or which side doesn't matter here. Okay, the result of the study is published, and you can actually Google this citation. If you go on corneal thickness and Google it, you actually see the full article. It's interesting. So here's actual data. Now these data are in microns. The thickness is in microns. Micron means 10 to negative 6 powers. So this number 486 means 484 means 484 times 10 to negative 6. That would be in inches. So that's how tiny that measurement is. So look at the thickness, corneal thickness in the normal eye for patient number 1, and look at the eye with glaucoma. The difference, 8. So the eye with glaucoma actually is thicker by 4 micron. That's 4 times 10 to negative 6 power, which is not much of a difference. Look at patient number 2, identical. So average difference, 0. This one, 492 versus 480, so thicker corneal thickness of the normal eye versus the eye with glaucoma. So from this one, 492 minus 480, that's 12 micron thicker. So let's agree, if the average difference is positive, means thicker corneal thickness for the normal eye. If the average thickness is negative, means thinner corneal thickness for the normal eye. We need that because the way the question is posed, I need to translate that symbolically. When we say symbolically, by the way, folks, that was on your midterm. State the null and alternative symbolically. This is what symbolic means. When you use symbols, when we do this for means, we use mu for means for the population. We don't use x bar for the sample. And that's what symbolic is in symbols. Okay. At the 10% significance level, that would be our alpha. Do the data provide sufficient evidence to conclude the average or mean corneal thickness is greater in normal eyes than in eyes with glaucoma? Remember, greater thickness. If you look at again patient number 3, greater thickness means when you subtract before minus after, you get a positive difference. And that's the motivation for my alternative. You see that? And remember, one hint I gave you when we first did hypothesis testing back in chapter 4. The alternative is not allowed to have equal sign. So however you have to make this make sense, your alternative has to be either less than, greater than, or not equal to. Okay, so if you find yourself putting equal sign in the alternative, you know you've done something incorrect. Now, my mu1, I'm going to call that my population with a normal eye. Population 2 would be the population of corneal thickness for the eye with glaucoma, or eyes with glaucoma. The null says, there is no difference between them. Remember the status quo, no change, no difference. So that means the average difference is 0. We are actually the researchers, this researcher in particular, is interested to show that actually healthy eyes have thicker corneal thickness. Okay, but the sample is very small, folks. Notice 8 patients. With small samples, it's very difficult to reject the null hypothesis. Very difficult. Whereas if this was a sample based on 10,000 people, he would definitely reject the null hypothesis. But with this small of a sample, I doubt if he can. And there you go, going forward. Remember, we just run these in Minitab. So, the average thickness, right in here, positive 4. Remember, a positive number means thicker corneal thickness for the normal eye. So, on average, the eyes that are normal are about 4 micron, that's 4 times 10 to negative 6 power, thicker than the eyes with glaucoma. That difference of 4 micron is not statistically significant. Look at the p-value there, 0.164. So we're not going to reject this null. That means the null, the status quo said, see, there is no difference between those two. And this researcher is not going to be able to reject that null hypothesis. And then I did an 80% confidence interval for this one. 80% confidence interval. That makes alpha 20%, half of that 10%. Okay, and that way, if you want to do a two-tail alternative from confidence interval, you could. But I just want 80% confidence interval. There you go. 80% confident. The average difference runs from negative 1.3 to 9.3. So that means the actual negative means thicker corneal thickness in the eye with glaucoma. So the average difference could be in the favor of eye with glaucoma all the way to the other side in favor of the normal eye. And 0 is in there. That means no difference. So what is our decision and conclusion? Our p-value is not less than 10%. So we're not going to reject the null hypothesis. And there is no difference in corneal thickness between the normal eye and the eyes with glaucoma. Now, let's run this in Minitab and we're done with this lecture. So, in Minitab again, let me bring up Minitab. Actually, it's too soon to go to Minitab, right? We need the data, don't we? So let me actually go to Excel. And in Excel, there you go. See, I have it right on this side now. So in Excel, as you can see, you can just type these in. You can just type, let me do it again, normal, and then input these numbers. Luckily, there's not that many data points. I didn't have to do this. Didn't take too long at all. So here's how you bring the data in. Now I'm just gonna highlight, right click, you can copy or do Control C. So I'm gonna copy this. I'm gonna bring up Minitab, and then let me move up my data window. Right in here, I'm gonna do Control V. V is in vector. There you go. And Control V will paste it, or you can right click. You see that? Right click. Let me show it here. Right click. It just keeps going up there. So anyway, right click and paste. So the data is here in here now, right? So let me again activate. I may be able to do this and get away with it. Yeah. Now let me change that viewing window. I'm going to go all the way from corner to this corner. Okay. So let's do a paired t-test on normal versus eye with glaucoma. Remember, we go to stat. You go to basic statistics and go down to paired T procedure. And this is data from before, but don't worry, if you left click once in this field, now because there are 4 columns, look what happens. See, you see these 4 columns. So I'm in this cell. If I double click on normal, it selects it. It automatically tabbed over to sample 2. See, I didn't do that. So I'm just going to double click on glaucoma. And there you go. And I'm not going to do any of the graphs for this one, but you could if you like to. And options. So let's do our hypothesis test. We want to say the eye with the healthy eye has thicker corneal thickness. So that means the difference was positive, right? Greater than. Okay. And there you go. And this is what this hypothesis test is. Let me lower this window. And there you go. That's how I got that 0.164 test statistic, the p-value. Now notice again, because this is a right tail test, this time the lower bound for confidence interval is that, but that's a one-sided confidence interval based on the alternative. I did an 80% confidence interval, so let me do an 80% confidence interval. I'm gonna go to stat, basic, down to paired T. The selections are fine. I'm gonna go options, change 90 to 80%, whatever you want, you may be interested in, but make sure you change the alternative to not equal in order to do a correct confidence interval. Hit OK, OK, and this is actually now the correct, this one is the correct confidence interval. That's the one I had in my notebook. Okay, and there you go. So it's pretty easy when you do it in a Minitab. And I believe with that, let me go back to my notes and let me resize this window. All right, and there you go. So we're done with this one. We did our conclusion, and this will conclude this lecture. So we're done with that section also. The section that we just wrapped up was section 5.2, paired samples t-test. Okay, so I'm gonna sign off with this one.